Let's look at one solution to the Tower Hanoi problem. When I introduced the problem, I sort of randomly moved cubes around, with the goal being trying to move cubes to the right as much as possible. The first move I made moved the yellow cube on top down to the beginning of stack of 1. And I'm going to denote the move here as 0 move to 1. The next thing I did was I moved the purple cube that was here to stack 2. This is the move 0 to 2. The final thing I did was move the yellow cube from stack 1 to stack 2. I'm going to denote this as 1 to 2. After I've moved the small subset over to stack 2, I started working on the next cube, the orange cube. The orange cube could move from stack 0 to stack 1, and then we begin moving everything else on top of the orange cube. The first thing that needs to be done is the yellow cube needs to move to stack 0, then the purple cube can move to stack 1, and then the yellow cube can move on top of stack 1 from stack 0. Only now can we move the big cube from the first position all the way over to the position in stack 2. This is our final position for that blue cube, so we're in good shape. Then we can go ahead and move the yellow cube over with the idea that we want to move the purple cube out of the way. But at this point, we can start to see that we're seeing a pattern of moves. The first thing we're going to do is we're always going to move something in spot 0 to spot 1. Then we're going to move anything in spot 0 to spot 2, and then from spot 1 to spot 2. So we see 0, 1, 0, 2, 1, 2, 0, 1, 0, 2, 1, 2, 0, 1, 0, 2, 1, 2. The only difference is we have an arrow at a certain place. So let's go back to this fourth move. Here we just moved a cube from the orange cube from stack 0 and moved it to stack 1. So 0 to 1. And the next thing we're going to do is we're going to move stack 0 to stack 2. So we know this is 0 to 2. But that's not what we did. We actually did 2 to 0. Because in fact, if we did 0 to 2, 0 to 2 would have required us to move this blue cube and put it on top of the yellow cube. So this is not a legal move. And in fact, here, we can't move 0 to 2. The only option we can do is to go from 2 to 0. What we're doing here is we found a strategy of repetitions inside the move order, where our rule is we're always going to go 0, 1, 0, 2, 1, 2, making the legal move at each case. So what we expect is that for the next set of moves, we're going to go 0, 1, and the 0, 1 is going to be in whatever direction results in a legal move. Can we move anything from stack 0 to stack 1? We cannot. Can we move something from stack 1 to stack 0? We can. So we know the arrow must run left. Next thing, we know that we need to go from 0 to 2. Looking at can I move the purple cube to on top the yellow cube? The answer is no. Can I move the yellow cube on top the purple cube? The answer is yes. So we know that it's going to be 2 is placed onto 0. And the very last thing, we know 1 to 2. Here, the orange cube, can we move 1 to 2? Yes. So we know the arrow must go right. We can repeat this process, but let's actually have the program complete this process and see if we solve the game by using this pattern. In the game's class solve function, I have a loop that's going to loop until the last stack has a size of 4. And while the last stack doesn't have a size of 4, I want to continually follow our pattern. I want to make a legal move between stack 0 and stack 1. I want to make a legal move between stack 0 and stack 2. Then I want to make a legal move between 1 and 2. I don't actually have much intuition on why this works, and we'll look at a solution that's much more intuitive as our second solution, but we notice this pattern, and we want to just test whether or not this pattern's actually going to help us solve this problem. The last thing I need to do is I need to write a function that calculates whether or not a move is legal. So if I need to do a movement between 1 and 2, I can either go from 1 to 2 or from 2 to 1. In this case, I cannot put the orange on top of the purple, so I have to put the purple on top of the orange. So I know the only legal move here is to go from 2 and move it to 1. I've defined a new function inside of game.cpp called legal move. And this legal move takes in 2 indices. These indices are the index of the stack that we want to look at. And let's look at the if statement. So if the stack at index 1 dot peak top, so if I look at the top cube and I just take a peek at it, and then I get the length of that cube. So I'm going to look at the length of this cube. This cube's length might be 3. And if that cube is less than a cube that is at index 2, so maybe this has a length of 2. So if 3 is less than 2, then I'm going to move index 1 to on top of index 2. So luckily the statement's false. 3 is not less than 2. So that means I'm going to move index 2 on top of index 1. So I'm going to move index 2's cube onto index 1's cube. So here, after this program runs, we expect a cube to sit on top of a cube. And there's only one legal move. So we're going to continually make these legal moves as much as we can, following the pattern 0, 1, 0, 2, 1, 2. And our program is going to decide which of those 2 moves are legal and continually run until we find we've reached a solution. I took off one little part at the beginning of legal move, and I wanted just to show you that code real quick. So what we see here is before we even look at the legal moves, we want to do a little bit of analysis to make sure that we're including the fact that we may not be able to peek on top of each stack. So at this point, we said we're going to peek on top of it and see what the top cube is. If the top cube doesn't exist, we're going to get an error because we can't look at a cube that doesn't exist. So here on line 44, I check to see if the stack at index 1 is empty. And if it is, then I know the legal move has to be 2 to 1. Otherwise, I check if the stack on index 1 is greater than 0 and the stack on index 2 is empty. And if that's the case, then the only legal move is 1 to 2. And only if I find that both stacks are non-zero do I go ahead and follow my logic earlier of looking at the top of both stacks and comparing. So the entire function has the logic to check whether or not any of the stacks are empty. And if one of the stacks are empty, we know that the other move has to be valid. If both stacks are not empty, we can actually then compare the top cube. The very last thing you may have seen is we made use of a move function. This function removes the top cube and places the top cube into the variable cube. And then the line 40 goes ahead and pushes that cube onto the stack at index 2. So we're taking the cube off a stack of index 1 and putting it on index 2. And that move function is simply going to look at those 2 indices and do the move without any checks, because we've already checked what order we need to move them into by how we're calling the move function earlier. So let's see how this entire program works, and let's see if this program actually generates a solution. So let's go over to the console. Here in the console, moving into CPP tower solution. I'm going to run make and running /main to run our program. So what we see is we see a whole bunch of output, and we know we see a whole bunch of output because after every single move, you'll notice in the source code that we print out what the state of the game was. So here at the beginning, the initial game state was stack 0 has 4, 3, 2, and 1, and all the other stacks are empty. And then we go our movement 0 to 1. So we move the 1 that was on stack 0 to index 1. Our second move out of our strategy is to go from 0 to 0, 2, and then 1, 2. And we see this repeats itself again and again and again. And the final game state is amazing. We got the stack 4, 3, 2, 1 that was initially in stack of 0 moved over to stack of 2. So one of the beautiful things about computer science is the fact that this is not the only correct answer. And in fact, this correct answer was something that only came to me as I sort of was working through the problem. And it didn't really intuitively come to me. And this solution isn't the solution that I would approach first. I think this is a solution that's simplest to code. But in the next video, I want to talk about the solution that I find more beautiful and allows you to see another way to solve the exact same problem, and both solutions are going to get the right answer. So I'll see you there.